Okay, welcome back everyone to day 2 of What's a Microcontroller with Python and the Microbit. With you again today are me, Andy Lindsay, along with Ari Alvarez and Stephanie Lindsay. Maybe by day 3, I'll get that starting slide right before start recording. Okay, so today we'll talk questions and answers first, and also some follow-ups. And after that, we'll talk about circuits and measurements. That could be a 4-hour session on its own. So I will just try to show you a few of the highlights. After that, we'll look at how to control the lights and the push buttons that you built on your circuit board for homework, or on your breadboard, pardon me. And we'll also talk about some of the concepts that are introduced along the way. For example, input, output, analog versus digital, logic states, high and low, true and false, signal timing, and some of the computer science concepts underlying how to make all that work with the microbit to make your circuits do cool things. And last but not least, we'll talk about the homework, where we'll be adding a servo as well as a potentiometer. That's kind of a knob you can twist, and then the microbit can measure its position. And then also the learn.parallax.com login. So that's going to be today. First of all, some follow-ups. I promised that I would show you inside the breadboard, that it was in one of the tutorial pages. So here we are in Try This Probing the Breadboard. And this is essentially one of the things we did on Monday. And I was at this page, but this student activity has them go through not just a couple of possibilities, but all the different ones that we talked about for connected and not connected, and adding a jumper wire across the row, after making sure that you've, I like how the magnifier works to make sure that everything's connected properly. And so after the students do more of this probing of the empty rows and columns, we talk about, okay, metal conducts electricity, and there are conductive metal clips. You may be able to see the little opening. So basically they're two little fingers that are pressed together. And when you insert a wire or part lead from the top, it actually presses those metal fingers apart. And there are 5 of those, all on a metal clip underneath the terminal strip rows. And then this shows, it's a little bit difficult to see. Let's see here. See if we can zoom in on this. Okay, now hopefully the little metal extension that jumps between all these little clips in the column are showing. And also going back to the rows, each one is insulated by a little bit of plastic on both sides. And so that's why if you plug 2 wires in one row above another, there's no connection. But if you do it in the row of 5, yeah, you've got an electrical connection. Does that make sense? Are we looking good there? Okay. Please always feel free to unmute yourself and shout out a question, or Stephanie will be watching the chat as well, and will shout out anything that she feels like I should probably stop and talk about. Yeah, we really appreciate your questions. We take notes on them and we make sure to use those questions, because if those questions are on your mind as we're going, they'll probably be on your student's mind too. And so we want to have them either in the student material or the teacher's guide. So that was inside the breadboard. Another thing that I'd like to just kind of go back to the previous workshop and talk about is simply that there's a lot of step-by-step learning that we're kind of skimming over. And so just as a way to try to give you an idea of the depth and detail of the tutorials, here we are in breadboard setup and testing. We're in the third activity, which is the first breadboard circuit. And what it shows here is a printed list of the parts, but it also shows a nice picture that has each part carefully drawn next to its schematic symbol. And so as we go through, you can draw the student's attention to things like, hey, look, here is a longer leg, a shorter leg, and a flat spot on the light emitting diode case. Well, the longer leg and the rounded edge here corresponds with this end of the schematic symbol. The shorter leg corresponds with this end. Resistors, incidentally, are not, so the light emitting diode is a directional device. If you plug it in backwards and apply voltage, it won't give off light. You can unplug it, plug it in forwards, then it gives off light. And the resistor current will flow through it either way. An LED is a one-way valve, but I'm getting ahead of myself because that comes later. So then another point is that in order to convey how a schematic works, what we do is we start with the parts, and this is going to go a little fast, so I'll just do this where I can control the playback. Okay, so here we have our three parts, and as each one is plugged in, we've got our jumper wire, and it's connected to ground here, which is connected by black wires. There's a ground pin going in, there's two ground pins actually going into the breadboard's blue column here through the edge adapter. And then so when we jump over here, that extends ground to this column. And then when we jump over here, it extends ground to that column. And then adding the LED, as soon as we add it, the schematic symbol appears. And then plugging in the resistor with just one end sticking up in the air, well, here's the one end sticking up in the air. And then finally plugging it into a socket by the red column, which is 3.3 volts. Now we have our complete circuit. And so this kind of thing, as we go, is intended to convey how, hopefully more clearly, how a schematic relates to the circuit a student builds. And let's see here. So another thing is then we are very methodical. There's a step-by-step, plug in the USB cable, make sure the light goes on. Then it talks about how it works. So this is things I kind of breezed past. And if you felt like you were maybe going kind of quickly on Monday, well, we were. And there's a lot of material for each classroom session that students can go through step by step to learn quite a bit more than we can convey in 4.5 hours. And here's another example of that, a light emitting diode. Again, here is where we talk in more detail about the names of the different pins on a light emitting diode. Again, how each pin and its shape corresponds with the shape of the schematic symbol. We also do that with the resistor. And you may have been wondering what those color bars were on the resistor. Well, that comes on the next page, actually. What this is simply showing is again, another way of thinking about the schematics, and schematics don't always have to be drawn vertically for lights. This one is drawn so that it shows more clearly how the connection works. We have our sockets by the red column here that have 3.3 volts. Here's our 3.3 volt schematic symbol. And then we go to the resistor, that's right here. Then to the light emitting diode, that's right there. And then all the way to ground for a complete circuit. Then we talk about the resistor color codes. And this is kind of a simplified way of thinking about it. In engineering school, that they talked about, instead of tacking a number of zeros onto your resistor value, it had to be, 10 to a power of that number. But the net effect is it's the number of zeros to add. So, so to keep it a little bit simpler at this introductory level, I just called it out as the number of zeros. So we have 3 stripes, or 4 stripes total. The first 2 stripes are 2 digits. And so if you look up red in our little table here, that's the number 2. So we know that the first 2 digits of this resistor's value, which is its tendency to slow the flow of electric current or resist the flow of electric current in a circuit. We have red, so that's 2, 2. Then the brown stripe corresponds with the number 1, and that is the number of zeros to add. And then the gold stripe is basically how accurate you can expect the value of the resistor to be over temperature. And also just kind of in general, they're going to vary. The values will vary a little bit, even just when you pull it out of the bag, even if its temperature is not different. And so this is good to 5%, which means 220 ohms plus or minus 5%. So these are informational things. And then of course, how current works, how electrons flow out of the negative terminal of a battery through the light emitting diode, through the resistor, and then recombine with a chemical in the positive terminal of the battery that is hungry for electrons. And of course, there's a separate chemical that has an excess of electrons connected to the negative terminal. And we always try to have the students do something, and it looks like this picture needs to be edited because this just shows the original. We need the brown, black, red for a dimmer light. It's a higher resistance value. Okay, so anyway, here is an example, and then there's always some assessment material. There's some practice material that corresponds with the assessment materials that we'll talk about on Friday that the students can use to practice here. And so there's some challenges of certain circuits to build on the breadboard along with solutions. And then you get a second set in the assessment materials. Stephanie, did you?
Here's a question that a student might ask. Do electrons flow from cathode to anode?
That really, that's a good one. It's funny because I looked that up the other day and now I'm trying to remember because it's one thing in chemistry and another in electronics. I'd better Google this one so I don't answer it, try to freestyle and answer it wrong off the top of my head.
Do you want to do that and send your answer out with the homework?
Okay, that's fine. In the case of the light emitting diode, going back to that, if I can get there. Thanks, that's a good idea, Stephanie. Okay, so here we are at electron flow. So in this case, in the case of the light emitting diode, current is considered to flow from positive to ground, or from the voltage source that's higher in value. Ground is considered 0 volts. And so there's a certain amount of current that is considered normally to flow this way. And that's attributed to Benjamin Franklin, who did not know about electrons at the time that he proposed how a circuit should be diagrammed. And so in reality, the electrons are coming out of the negative terminal of the battery into the light emitting diode's cathode, out its anode, and then the rest of the way to the positive terminal. So that I can tell you about LEDs. I'm kind of fuzzy about the different applications, especially in chemistry, because it's been more than 20 years since I built a battery in a solution in chemistry class. Yeah, it was a lead acid solution. Great fun. Let's see. So that is a little bit about the learning schematics that we didn't really talk about as we went on Monday. It was mainly just trying to get the board to get your prototyping system set up. One other thing is I said, okay, I'm going to show you why it's better to have a hex file, or we're going to be using hex files later. And so here is an example from the Cyberscope. Okay, so if we go to cyberscope.parallax.com and then download Try Cyberscope, which you probably did for your homework. I'm hoping everybody did that. Save link as. Save. Okay, and then we go to python.microbit.org. Drag and drop Try Cyberscope in. Click connect, select the microbit. Click flash, and then click disconnect, run over to the Cyberscope, click connect. You might see CMIS DAP or BBC microbit. Hopefully you see the whole thing. And great, we have this display going on here. And let's say, for example, that once we get to the voltmeter, ammeter, and ohmmeter test, which is coming up in a few seconds here. This is currently just a sine wave and an exponential decay, which are both very common in electric circuits, which is, but obviously, as you were doing this at homework, there wasn't any circuit doing the sine wave or the decay. So let's say that here there's a complaint that we need more time to look at each of the values and make sure that they're readable. Okay, so we'll disconnect and we'll go back here and change our code. So let's change these sleep 250s to sleep 500s. And that will essentially slow everything down. And don't worry about the details of this. It's further down the coding road, really. But just suffice to say, okay, we slowed it down. Now everything's going to take a longer time to display. And I don't know if it's going to be worth showing that or not. Let's see how long it takes to get to connect. Okay, so now it's going a little bit slower. It's not rushing through those voltage and resistance, and then not shown was current measurements. That would be the next time around in the test cycle. Okay, so great. We have a program that is better, and so we'll call it Try Cyberscope more slowly. Give it a name, and then click load, save, and download project hex. That's the normal thing to do. Now, there was a question of, well, okay, why don't we just download the Python script instead? Well, first of all, we get a warning that it's could be a malicious attack, which in this case it's certainly not, because it's the script we wrote. Now we have Try Cyberscope as a hex file and a Python script. So let's say that after refreshing the web page, we lose all our work that way, and we get a default script. If I try to load Try Cyberscope.py, yeah, there's the script, but if I connect and try to flash, there's going to be an error when I open serial. And it'll also display on the microbit itself. So it says trace back on line 4. We can't find that module named multimeter. And so looking at line 4, from multimeter import. So I mentioned that you could add modules to your project. So let's take a look at how that looks. This time I'm going to open try Cyberscope more slowly .hex instead of .py. The code looks the same, but this time, if we go into load save, we'll see that there's the main file, try Cyberscope more slowly, and the Python script. Whereas when we just open the script and take a look, oh, that was weird. Load save. I'm going to browse and make sure that I open the Python file here. Okay, so now let's hit load save. Huh. I really do not know why I have two files. I'm going to reload the screen. This almost looks like some unusual thing in the Python editor itself. So now I just reopened it after refreshing. Yeah, see, here's only one file. So that's what I meant to show you. Sorry, that wasn't the best of demonstrations because for some reason, if I have a window open, cancel. All right, so starting from scratch here, yeah, there's only one file when I open the Python file if I'm starting from nothing. Apparently, if I've opened it once as a hex file, where it has that multimeter.py module payload, then I can open a script, but I really wouldn't want to depend on that. I just prefer to always save everything as a hex file, because then you can be assured that you'll still have that multimeter.py module with your project. One last thing while we're at it is that we've been using python.microbit.org/v/2. Well, there's a kind of a neat thing. I don't recommend switching over to it just yet, but there's a beta version of the microbit editor that will eventually be version 3 instead of version 2. And what's cool about that is if you open a hex file here, unlike the previous version, you can actually look at the project files and see here's main.py, that's try Cyberscope more slowly, but here also is multimeter.py. So you can actually look at the code inside the module to see, for example, here is where some of your code passed through on Monday when we were using the voltmeter to measure the volts across the different parts of the LED circuit. Just a nice little side note there. But for most of our work today, it's really going to be a lot easier to go through V2 because that's what's documented on the in all the chapters currently. Okay, so that's it for the follow-ups. Any questions before we move on to testing those circuits we built? Okay. Again, please feel free to chime in.
So, can I ask quickly, Andy?
Yes, please.
We went to Cyberscope. We tested the Cyberscope. And which other code did we run in Cyberscope outside of just that oscilloscope and the other one?
Oh, okay. So on Monday, what we ran was see here. On Monday, we ran 2 different things that had the Cyberscope module. The first one was in, I need to zoom out a little bit here. Okay. Let's see, the first one was, here's a way to go back to the main table of contents. And when we go back there, breadboard setup and testing is where we did the continuity testing. So that was first electrical connections. And then, so we downloaded this continuity tester script. Let's see here. And after downloading it, we ran it. And this one didn't actually display anything in the Cyberscope, but it does use the multimeter module. So for example, if I open the continuity test script and then look at its contents, you'll see that it does have multimeter.py in it. And there's a
Yes, thank you.
Continuity. Okay, so there was also another one which was in electrical measurements. We just barely touched on measuring voltage with a voltmeter. And in that script and test, we had measure volts with Cyberscope. And what that did is it allowed us to measure. Basically, we started with 0 volts, then measuring all the way across the circuit, we have about 3.3 volts. Measuring across the resistor, it's about 1.2 volts. Measuring across the LED, it's about 2 volts. And those 2 values, the value of each component should add up to the total value applied across the circuit of voltage.
We have a question about homework.
Okay, thank you.
Yes.
Was the homework just to build the circuits with the 3 LEDs and test that Cyberscope is graphing with no probes connected?
Hopefully 3 LEDs and 2 push buttons. And then yes, testing to make sure that the Cyberscope would display okay for you. The idea was I didn't want to overwhelm anyone with homework midweek. It didn't seem like a really good time to really pile on lots of stuff to do. So so I wanted to make it just a easy, gratifying thing. We got the circuit built and kind of like this. And then and now we're ready to test it. So with no further ado, actually, let's try it out. And as you can see, I'm clicking around and visiting certain spots within the student materials. They are very methodical and step-by-step when they're used in the classroom as opposed to a short workshop. Okay, so in electrical measurements, no. In LED lights, what I'd like to do to test our LED lights is start with the script, and this one is not going to have any modules in it, so I can just paste this one straight into the chat. I'll paste both the web address and the chat. Paste. Okay, so that's the web address where the script came from. And then I'll also paste the script. I just remembered I'm not on a Windows machine, so I can't copy 2 things and then paste them both in, or at least I don't know how to do that on a Mac. Okay, so here is the actual script. And so what we would want the students doing, of course, is to be setting the tutorial side by side with the editor and typing it all in. But in the interest of time, what we'll do is copy and paste it in and just talk about its features a little bit. we have a while true loop with 4 statements indented. And I think I might want to wait a little bit on going into the details of that because there's a good graphic coming up. But suffice to say, there's going to be 4 statements that are repeated over and over again. One that turns the light on, one that turns the light off, and between each is a ½ a second delay. So if you hit connect, so if you go to python.microbit.org/v/2, paste that in.
Here's a question.
Uh-huh.
Is there a way to retrieve a script that has already been flashed into the microbit?
I do not know how to do that. I've never seen a solution for that. You could try Googling that one. And if somebody, there may be a microbit aficionado amongst us in the audience. If anybody knows a way to do that, by all means, let me know. But I don't think that's something you can do. Let's see here. Yeah, let's add that one to the list of questions for an email reply. I'm thinking that there may be a way using the mu editor. I know that, for example, you can download multimeter.py from an existing project, but yeah, I'm not sure. I don't know off the top of my head. So let's add that to the questions list. Okay, so cathode, anode. And then retrieve or upload script from microbit. Okay.
The reason I asked that is I just want to know what's in my microbit at the time I plug it in. Let's say I forget what's in it. You know, I don't know.
Oh, yeah.
It's supposed to run.
Yep, that's a really good question. And
it looks like Simon has posted a solution.
Oh, really? Got to get to the
support
chat for
article.
that. Thank you, Simon.
Thank you.
Okay, so let's see here. So for anybody watching the YouTube later, they can pause the screen to see the web address of this article. Okay, so let's use this script to test our light that's connected to P14. So that should be the yellow light. Oops. So after loading the script and making sure that you're connected, and then flashing the script, we want to see the yellow light blinking at a rate of once per second, or 1 hertz in electronics speak. So pop quiz, how would I double the speed of this blinking light?
Cut the sleep time.
Reduce the sleep time.
Reduce the sleep time. So 250 and 250. I don't know if that's actually gonna, let's keep our fingers crossed. Is that conveyed across the Zoom? Is it visible as blinking twice as fast? Okay, good. All right. So now another question we'd have would be, how can we test the green light that's connected to the P13 socket here? So we've got the yellow light with the resistor and it's going to P14. So now that's toggling on and off. How would we do the green one? Any answers in the chat, Stephanie?
Not yet.
13. Yeah, 14.
Here we
13.
go. bunch of answers at once.
Oh, they all flooded in.
The whole
Okay.
code.
Yeah. Okay. So the answer to that is right now we're turning the yellow light on by saying pin 14 dot right underscore digital of 1. And to turn 13 on, we'd want to say pin 13 dot right digital of 1. And then likewise, to turn it off, we want to say pin 13 dot right digital of 0. And flashing that, we can see that the green light is now the one that's flashing. And I'll slow mine back down to 500 just to make sure it renders for everyone.
I can make a couple of comments.
Yes.
When I was putting in this and looking at the schematic, and it said P13, P14, I was looking at the breadboard for 13 and 14 rather than the controller, which eventually I figured out, oh, those are the pins you're talking about.
Ah, yes.
A student might confuse the pins with the board.
Right.
Right? You say it's pin
And
13, but it's going in my breadboard at number 17. What are you talking about, right?
yeah, so let's see here. You know what? I don't really have a great picture of that.
Right.
I can't think of where in the tutorials I have a good picture of that. It's certainly stated in words.
All right, I understood it. I looked at the diagram, but then I looked at the diagram.
Yep.
The diagram was saying P13, 14, and 15. And I said, I had nothing in those. I had 17, 6, and 9.
Yeah.
And
So
then I realized it. I'm just saying how a student could,
oh yeah.
And the
Yeah, I see that.
second question I have, how do I stop it? How do I stop a program? When I put it in, the heart get coming up, hello and heart, hello and heart, hello and heart. Do I just yank the cord?
Well, there's a couple of different ways to do it. The first one would be to basically, all right, so let's, so I'm going to right click my tab. I guess I'll disconnect here. We'll right click the tab and duplicate it so that now we have a second instance of the editor. And what you can do is instead run a program that just sleeps. That's actually what I did right before the workshop because I didn't want to have anything displaying on my microbit that would be drawing attention while speaking. And so I just basically flash in, see, I mean, you could even make it smaller, like you could just say basically sleep 2000 or print hello, because print hello would only appear in the serial terminal. So you know print hello.
But there's no on and off switch on the board itself.
No.
Okay.
And so this is one way to toggle between, and especially when the students are experimenting with sound, make sure to get them primed so that after they've done their sound thing for 20 seconds, they can run this program. Otherwise, make sure to have some headache medication at the ready in your teacher's desk drawer. Okay, so let's see. Yeah, that's the best way I know to stop the program. You might just be able to even flash that. Yeah. So pass just means skip this line. And because I don't think that if we flash it with just from microbit import, we get anywhere. Let's see if that generated an error or not. Oh, no, that's great too. All right, so yeah, just an empty program will be enough to turn it off after it's running. Okay. Now, where were we? Let's see here. Ah, yes. So before moving on, what I'd like everybody to do is to make sure to test there are blinking lights on pin 13, pin 14, and pin 15. So there's several different ways you can do it. You can do it once at a time, like I did. You can also simply copy and then paste. Make sure your indentation is correct. And if you do that 3 times for each, you'll be able to test all of them. Okay, I'd like to bring your attention to one thing real quick. Going back to the having a program that's ready to stop the microbit. If your students have 2 tabs open, in some computers, and mine is one of them, notice that I'm connected here and disconnected here. And now I want to run this program, and I hit connect, and I'm merrily on my way until it tells me that another process is connected to the device. And the student might come and say, hey, I can't get connected, and not have the whole story behind what they saw. And so this is basically trying to tell us, hey, close the other connection before you open this one.
There's a comment down here.
Okay.
I believe we could have a while loop based on button A, B, or touch instead of a forever loop, true, to start and stop the program.
Okay. So that's a good idea. So it would be while, let's see, pin. Oh, I forget the button commands because I've been using the breadboard so much. Okay, this is a really important resource for everyone, so I'll paste it in the chat. Okay, let's see here. So buttons. Okay, so we can do while button is not pressed. And that's button A, I think. Let's do button A. Yeah, microbit.button A. Button A is pressed. Something like that. Okay, so now my lights are off. And if I press button A, there we go. And then the other important thing to think about there is that you can use the reset button, which again is underneath right there by the USB cable. So if I press and release that reset button, having the while button A is not pressed at the beginning as the gatekeeper, again, I hit button A and there we go. And then reset to turn the program off. That's a great suggestion. Thank you so much. I'll go ahead and paste this one into the chat. Let's see, here we are. paste. You guys can all try that one. Now, we also have some push buttons on the breadboard that we could use, but I think that this is a particularly good use. Okay, so I see how do we use chats?
How do we save the chats? I don't think that we do save the chats.
Well, we do save the chats, but we don't really publish them.
No. But I think you should be able to copy and paste out of them if there's code that you want.
Yeah, Stephanie, is the chat visible to the other? Is my chat visible to them right now? I dragged it onto the presenter screen.
Sorry,
don't-
quick note, if you are on the computer and you have the chat open on the right side, you can save the chat like as a text.
There's so
okay,
for me,
great.
there's 3 dots on the lower right. And when you click that, you can select save chat. There we go.
Oh, great. Thank you. I
Yeah,
didn't
thank
see
you.
that.
All right. So running that program, that script, how are we doing? Has everybody got 3 correctly connected lights? They're all going on and off after pressing and releasing button A. Only got 1 2 3 thumbs up. We're getting better here. Give you another minute.
So, okay. So the previous code that you posted in there, while not button A is pressed, pass, that is supposed to let the lights blink while the button is pressed or while it's not pressed?
That's a good question. So what's happening here on lines 5 and 6 is while not of button A dot is pressed. So we're saying essentially while button A is not pressed, this is a Python way of saying it. Do nothing. So pass, which I used earlier, is a way of just saying, skip to the next line. And the reason I have it here is because if we don't have it and we flash, there's an error, it causes an error. So that's just one of Python's peculiarities, is that it won't just automatically sit here in an endless loop, like say, for example, C language, which would the equivalent in C language will just sit there on that line. But with this, we need to do something, and you could sleep or just pass, which is, forget it. That's kind of like a non-statement.
Could you run it and show us what buttons you press to make that do something?
Yeah. So, okay. So right now, nothing is happening because I ran it and it's stuck in this loop where it just keeps on, skipping this particular statement because the button A, which is this button, has not been pressed.
Okay.
And so when I press it, now it is then, instead of being not pressed, it is pressed.
But your
And so
lights
when
aren't blinking.
Well, because I haven't touched the button yet. So now I'm going to press and
okay.
release the button. So there we go.
Okay. And so you can't turn it off with A again because you don't have that coded. But that's okay.
Yeah.
Just making sure I'm understanding what this code is supposed to do.
Yeah, so there is a
questions.
restart thing in the microbit.
Okay, I think just demonstrating what you did is working. Some people were not sure what it was supposed to do.
Okay.
So I think we're good.
All right, because I think we can also say.
I don't want to get you off track.
Okay. I don't know whether it's microbit.reset or reset. So I press button A. Okay, that goes. Oh, interesting. Huh. I'm gonna have to tinker with that one. I'd better send that one to everybody after some experimentation.
Okay,
But this would be a way, if you have something in your main loop, you could detect if another button was pressed, and then it would simply just restart the program and send it back to infinite waiting here.
we have a calibration question if time permits.
Okay, let's try it. I'll either pass or answer.
Bob, did you want to present your question? Maybe not right now then.
Bob is still muted.
Oh, hang on.
there you are.
I found
Okay.
the unmute. Okay. In the summer, I'm going to be working with 30 kids.
Mhm.
Mhm.
So if I do anything and lose any of those kids, it'll be 6 kids, 7 kids, 9 kids.
Yep.
So what I wanted to know is, when I checked into the session today, did I have to recalibrate my microbit card to participate today? Or once I calibrated it the first time, I would never have to worry about that again?
By calibrate, do you mean that quick little test we ran in the first homework?
Yeah.
Yeah, that was basically to make sure that that your microbit and the web browser on your particular computer would talk to each other. And so the reason I send that out as the most important thing to do before the workshop, well ahead of the workshop, is because what that does is it prevents folks from being stuck during the workshop if it so happens that their computer had some kind of peculiarity that would not let their microbit and their python.microbit.org editor communicate. So it was just a thing just to make sure that everybody had their microbit functioning properly with their Chrome browser and the python.microbit.org editor. That was all it was for.
Okay. Is there a super quick test that a teacher could do right before class just to say, okay, everybody's all set, let's keep going?
Well, it depends on what particular things you're doing. What is the age group you're working with, Bob?
It's going to be middle school kids in the summer.
Uh-huh.
And the thing that I would love to be able to do is to see that everyone has a light that is turned on. Then I could
Yes.
say to myself, okay, it's not going to be a connection problem. So here we go.
Okay. Well, normally just to make sure the microbit is working at the beginning of class, when they open their browser and go to python.microbit.org. Okay, so the first thing that comes up when you go to python.microbit.org is the hello world example. And so you could just tell them, hey, make sure to load that in, and let's make sure that your little display shows hello world and then a heartbeat. So that's the quickest way I can think of to do it.
Okay, that would do it. Thank you.
Certainly. These are great questions. This is, I'll need to go back through this recording for teacher's guide material. Okay. Now, let's see. The other thing that you probably want to test is your push buttons, and not the ones over here this time. We want to test the ones that are built right here. So I've got a bunch of programs ready for you guys in the learn tutorials. And so I think that, here we go. But for a quick test, and then we're going to change gears and do a little survey of some of the material that we skipped again. For a quick test, build and test a push button in the Sense Push Button Presses chapter, going to Script and Tests. This script right here is a nice one to test the lower push button connected to P6. And before I paste it in, let's make sure everybody's got their eyes on the screen. Okay, before I paste it into the chat rather, I'll paste it into my browser. And again, if possible, we want the students to type in a copy of what they see here. All right, so here we are with the script. I'm going to show you what to do. Click connect, click flash, then click disconnect. No, I'm sorry. Click connect, click flash, leave it connected, go to open serial. And what this is going to show you is the state of that this pin right here is reading, P6 going to the push button circuit. And you can see right now that it's not pressed and it's telling you the state is 0. Now, when I press and hold down that push button, notice that now we see the state is 1. And whatever you see at the bottom of the terminal is going to be my current pressing state. So pressed, released, pressed and held, released. So if our circuit here is correct, we also want to make sure to test the one connected to P9. And so after testing P6, you'll want to change this 6 to a 9 and that 6 to a 9. With that said, I'll go ahead and copy and paste over the I lost my chat again. There you go. Oh, and real quickly, you might want to also save your current work. So if you've got this file in one window, go ahead and save it as something like test lights. Load save, download project hex. That way you'll have a copy of it in your downloads before pasting this over. You can also, of course, open a new tab. Just make sure that only one tab is connected at a time. So I'd like everybody to now go ahead and test both push buttons. Never sure. That was some pretty strong feedback. Somebody's got 2 computers up. Normally that happens if you are attending Zoom on 2 computers and one of them becomes briefly unmuted. Okay, so now that I've got my pin 6 test, we'll go ahead and try changing both instances of pin 6 to pin 9, flash it again, and open serial. And this time I want the upper push button to give me the 1s when I press and hold it, and then 0s when I release it. Okay, so it looks like this this circuit is good for trying out some other applications.
We have a comment, nothing happens.
Okay. So normally if, does it display only zeros? Is that the nothing happens? Is that when you've opened the serial and you press and hold the button, it still displays state equals 0 as opposed to switching to state equals 1, or is there no state being displayed?
Mark, do you want to unmute? Julie says she gets no state displayed when opening the serial. Nada also is getting no state displayed.
Okay, so that is normally,
Because of not disconnecting.
well, I was hoping to get those weeded out by sending out that little test that we did preparing for the workshop. Because
We do have, Richard says it's working for him. So, and Julie did the test and it's still not working for her.
Did it work on button 6 and not
Oh.
9, or 9 and not 6?
Julie is on a different computer than on Monday.
yeah.
Hmm.
Julie's computer on Monday had some of the most spectacular symptoms I've seen.
Well,
I'm-
actually, Nada's is actually displaying random letters. That might be even more spectacular.
Oh yeah, that's pretty good. Julie, make sure you do not have a Cyberscope on anywhere. Close other instances of your microbit editor. And also, if you happen to have added this while not button A, if you still have that at the beginning of your program, that would account for it. You need to press button A in order to start getting something.
Oh, they discovered that my Monday computer was connecting to the serial port.
So I think we'd probably better plan to talk about that one after the session.
It was okay. Oh, Nada has hers working, and Julie says that it was assigned to multiple ports and it's fine now.
Oh, wow.
That was-
Oh, excellent. So, okay, good. So that means that like if you click the lock, you might have had, I don't know if that's what she means by multiple ports, but you can, in some cases, remove these and then unplug and reconnect if you're not getting any response. Sometimes also just unplugging the microbit and plugging it back in will suffice as well. Okay, so real quick, now that we've tested our push buttons and lights, let's I'm going to skip back to some of the material that we did not, that we're kind of skipping over. Back on Monday, we did measure voltage, and I talked about measure voltage earlier. So we talked about building the circuit, testing the voltage. And another thing that is introduced is Kirchhoff's voltage law, which is, the amount of voltage applied across any number of elements connected end to end or in series has to be equal to the voltage that is measured across each of those elements. So here we have 1.15 and 2.05, and that adds up to 3.3. Now, there's more to this particular chapter of electrical measurements. So we also have, in addition to voltage, which is what we did, we also have resistance measurements. And we do a lot of different measurements on resistance by building a circuit that is different from the voltage circuit. So we modify, I don't know where that was, measure resistance. Okay, so here's the circuit. So we show how to build this little circuit right here. And then note that we connected, that the students connect the clips, the alligator clips differently from the way they did previously. And then after they've built their meter, what they can do is go through and measure the resistance of, say, a single 220 ohm resistor. But then they go on to measure, and here it's 218, and that's within the plus or minus 5%. And then they will continue on to measure a number of different resistors. And this time it's a 1 kilo ohm resistor, or 1000 ohms. And here we have 994, nice and close to 1000. And so they get the chance to measure resistance. They also learn about, okay, what happens if you connect two resistors end to end? And thankfully, it's nice and intuitive that they add up. It's less intuitive if you connect them side by side. This is called in parallel. And here you get, in this case, half the value that you had of the two elements instead of them added together. And it talks about the math for that. And so then there's, as usual, questions, exercises, and projects. Those are solved. And the students also learn the math behind these as they're going. Then we go into measurement units, about the metric prefix like kilo, micro, kilo for 1,000, micro for 1/1,000,000th, mega for 1,000,000, and how that relates to a regular counting number. And so we do the whole thing about SI, System International units, metric prefixes, listing them all, and then explaining how you can take kilo and replace it with times 1,000, or you can take milli for M and replace it by times 1/1000th. And then we even do some chalkboard explanation of how to do the conversion. Now, in addition to that, we've got Python. And so you can actually make scripts, and the students do run an example script that converts one direction. And then they are challenged after learning how it works. So this is how the script works. Then they are challenged to convert the other direction, to say, well, given an unwieldy number, can we take that and make it into something smaller? Like instead of 38,000 hertz or repetitions per second, we have 38 kilohertz. So they get to learn that and how to do the calculations. And then after this, they use scientific notation, and I'm looking for the script. So here's another conversion script. I guess we're not challenging them to do a script there. There's measure current. And again, Ohm's law is where I was thinking that we were going to challenge them to do a variation on the script. So for measurement units, they just got to see how to do the script. And then current measurement is another one where they have to change the measurement circuit before taking the measurements. And so here they have to add a little 50 ohm resistor, that's red, black, black, right across the two 3-pin headers where you connect the clips. And so I'm pointing that out because I did have a question from an earlier workshop where somebody said, well, yeah, I tried to measure current, but it didn't work. And the reason it didn't work was because he still had the voltmeter circuit set up. And so this is the ammeter circuit right here. And then you can use it with the Cyberscope's ammeter. Then Ohm's law is kind of a staple in electronics, and there's lots of curricular checkboxes in terms of math and science that are involved with Ohm's law. And what we do is we start out with a script that allows you to use Ohm's law, which is basically says, well, the voltage is equal to the current through the circuit times the resistance of the circuit, or of the component, I should say. And so that's looking strictly at resistors. And so they experiment with resistors. But the main thing about Ohm's law is we already just saw from measuring current that we had to change the circuit in order to measure current. Well, to get around that, if you want to find out how much current is passing through a resistor, well, if you know its resistance value and you've measured the voltage across it, you don't have to change up your circuit down here by where the alligator clips go at the base. You can simply say, oh, well, I know the voltage and the resistance, and then use this version of Ohm's law to calculate the current. And so we go through various example scripts and then challenge the student, okay, after they've done the math to solve for it, write a script to solve for it. And here is a your turn where they've already been given two versions of the script where, so we started with a script that basically does the calculation I just explained, where it calculates current given voltage and resistance. Then after learning some more details about that script, they're challenged to modify the script. And this is a picture. It's not a solved script like the one on the previous page and this one right here. And so this at least forces the students to put their hands on the keyboard and make a change, which will help facilitate learning how to write the scripts. Then after that, they're challenged to use one of the other variations of Ohm's law to, given the current and the voltage, to calculate the resistance that must be in the circuit. So these are examples of electronics lessons that don't happen in a lot of microcontroller curricula, because we try to keep it, most of the other lesson sets tries to keep it more qualitative. And so here we have a chapter that's focusing on the quantitative. Okay, so in the remaining time, let's have a little bit of fun. Let's start with setting the brightness of a light. Go ahead and paste this one in.
I have a question
Yes.
that came in. Do these scripts for calculation accept input from the keyboard?
Yes, they do. In fact, it's all done using input from the keyboard. That's a great question. Let me go back.
If so, is there something necessary in the script to do that?
Okay, yeah. Going back to, okay, so Ohm's law script and tests. So we'll take this example script right here and just run it. Oops. Okay, so this is the first Ohm's law example script. And close serial, disconnect. All right, flash, and then open serial. So we're entering volts. So 100 volts, and then enter the resistance. Let's say it's 50 ohms. So this is going to be a whopping amount of current, 2 amps. That's a in your car level amount of current. So as you can see, 3 3.3 volts, 220 ohms. So 0.015 amps or 15 milliamps is more like the kind of current you see in your projects here. And then to answer the question about how do you get the input from the terminal into the microbit, it's called an input function. And so you use the word input, and then you can add a message in between parentheses, and then input returns what you type on the keyboard. Now, to use it as a number, you have to take that text that was input, and if you know it's going to be a number, you can say float of text, and then that returns the floating point equivalent of the number you just typed in. So that's how that works. And again, this is all part of the lessons. And thanks for asking, just to make sure that I can give everybody a good, clear picture. And we were going to do LED brightness. Did I paste that in? Yes, I did. So how's that brightness look? Okay, so with the camera, it looks like a flicker, but as you're looking at it with your eyes, we want to see the light starting out fairly dim as a result of the 128, then a quarter brightness, 256, half brightness, 512, and then max brightness is 1023. Is everyone able to see that on their light? Okay, good deal. So, there are, let's do one more from the brightness. I think under how it works, we'll have a fade in, fade out. So that's going to make it go kind of evenly. And this is a script that the students have to enter. So what I have is, I have a hex script that I'm going to download, open, and okay, so basically this link is going to take you to a download page, and what you can do is download this hex script. And so it downloaded right there. And I'm going to do that in the.
There's a bunch of comments coming in.
Okay.
Let's see. I cannot see 128, but other three are distinct. Is 1023 the brightest possible? 128 is very hard to see, but it's there.
Yeah, 128 is pretty dim. That's like 1/8 of the regular brightness. And if you're looking straight down on the top of the dome of the light emitting diode, you might be able to see it more clearly.
Will wrapping your hands around it help?
Yes, thank you to whoever chatted that. And yeah, if you wrap your hands around it and look down, that's another way to see it. And let's see. So there was another question. Is 1023 the max? Yes, 1023 is the max of brightness control. 1024 would be if you simply said write digital of 1. So that's what we use to turn the light on. So it would be pin 14.write digital of 1. So that would be 1024. Because what it does is it flashes the light on and off at 50 times a second. And it's 128 10/24 of the time on here, or 256 10/24 of the time on there. And that's what gives us the sense of brightness. And again, there's lots of material that goes into how setting the brightness works. More about the difference between analog and digital values. And of course, there's always the self-check along with questions, exercises, projects, and their solutions. Let's see here, we have 8 minutes left. Let's do something that uses the push buttons. Yeah, I didn't get to the demo of push buttons on the oscilloscope. So second push button, 2-button control. Let's try 2-button control. Okay, I'll paste you this link in just a second. Or actually, I'll just download it, open it, and paste you the text. Okay. And then chat. And paste. There. Okay, so this is a script that will allow you to control a light with, or actually all 3 lights, I believe, with buttons. So essentially what happens here is if you hold down the lower button, the lights will turn on and off in a pattern that goes downward. And then if you press and hold the upper button, the lights will flash on and off in a pattern that goes upwards. And in the push buttons chapter, there is also ones for making the light brighter and dimmer by pressing and holding these buttons as well. So somebody give me a thumbs up once you've got it working. Good. Nice job, Chad. Thank you, Alexia. Is that right?
We have a very neat, like a little traffic light.
Well, and yes, as a matter of fact, as for projects, that's kind of a lesson in, hey, there's such a thing as an actuated traffic light. So can you set up the button presses and cause it to go from red to, or from green to yellow to red, just like a traffic light does? And that is why we chose these colors and the push button circuits. That all builds into that real world example. Thanks for mentioning it. Another thing to mention is that this is the first instance of a list that was used, and all there was basic stuff like decisions and remembering with variables that we went over initially in the homework before the class started. And so while true might look familiar, as everything below this happens repeatedly over and over again, but at this point, lists, or somewhere along the line before we got here, lists were introduced. And what this code example does is it increments an index and uses that index to choose either pin 13, pin 14, or pin 15. And that's why you're able to press and hold the button and increase the index to go for a higher number light, or decrease the index to go for a lower number light, and it picks which pin it's going to turn the light on with. And so that's an example of another computer science concept that we add in along the way, along with the electricity and electronics that we build sequentially with coding concepts as well. Now, I think what I'll do is I'll just plan to start off with a Cyberscope demo of the push buttons at the beginning of the next session, because what I'd like to do with the remainder of this session is talk about the homework. So for the homework, you're going to be grabbing a servo motor, and I'll send you links to these slides. Did that work, by the way? Can I get some thumbs up or down on, okay, so you were able to follow those links and they took you straight to the right slide? Oh, that's great. Okay. I'll send you links to these slides. So these are the parts you're going to be gathering. You're going to gather the battery pack, the servo. Inside the package with the servo, there's going to be this little armature that in servo speak, for whatever reason, they call it a horn. I don't know the history of that. And we're also going to grab out of our kit the potentiometer, two 220 ohm resistors, 2 red and 2 black jumper wires. And we're going to use that to add these circuits. So note that I have the circuits that we've been playing with today grayed out or partially transparent. What that is supposed to tell you is that they're still there. Don't tear them down. Make sure to leave the existing circuits that you have on there. They're still visible, albeit transparent. The reason they're transparent is because we want to direct the student's attention to the circuits that they're building, your attention to the circuits that you're building as well. And so that's going to be this one right here, this potentiometer dial circuit. That's for adjusting. You can have a rotating adjustment. And then up here is the servo motor. And we're just going to have you connect these, not test them. There's a 3-pin header underneath this servo motor. So you're going to push a 3-pin header into these sockets B, 3, 4, and 5. We'll get a 3-pin header, and then you'll plug the servo. It has a 3 sockets in its little plug, and you'll plug that right down over the 3-pin header. One last thing I wanted to do is with the servo, before we get started, this will open the doors for a few interesting things on Friday. So what we're going to do is find the servo in our kit. Now, for that matter, we'll just go ahead and grab the batteries. Now, do not load the batteries into the battery pack just yet. So we'll just have you building it. And then the servo looks like this. It's in a bag. The potentiometer looks like this. And I'll skip the resistors for now. What I want you to do, though, is find your servo and go ahead and take out the servo and then the single armature. So we're going to take the servo out. And then here is the little pointing single armature. And you can see you've got a lot of choices, but there's going to be a reason for this, because the main thing we want to do at the start is emphasize that a servo can pick a particular angle and hold that angle. And so just as a warm-up for Friday, what I want you to do is just arbitrarily attach the armature by pressing it down on top of the servo. Like so. And then gently rotate it to its most clockwise position. You'll feel it stop. As you rotate it clockwise, you will feel it all of a sudden start to resist, and don't push against that. Once you have found that clockwise limit, okay, it's actually right there for me. You can, what I want you to do is take the servo horn back off and then place it back on pointing to the right. So what that's going to do is give us a all the way clockwise position of basically 0 degrees. And then this is going to be 90 degrees. That'll be 45. And then the other stopper, now it should be at 180. I don't know why this is. That's interesting. This one stopper is not, oh, there we go. There it is. So that's the limit on the other end. So that is 0 degrees, 45, 90, 180, and then the counterclockwise limit. So make sure to get your servo horn attached so that the mechanical limit is just below 0 degrees. So there is actual 0 degrees. There is the mechanical limit. Okay, so that's one thing to do with the servo that is explained in the tutorials, but it'll make the experience better on Friday to have that done ahead of time. And then build the servo circuit, build the potentiometer circuit, leave all the circuits you built today still connected. And then the last thing for homework is just to either go to learn.parallax.com and log in just to make sure you can do it. So if you have a learn.parallax.com login already, go ahead and type in your username and password and hit login and make sure that it confirms that you're logged in. Then you can log back out. If you can't remember your password, there's a request new password button right there, and it'll email you instructions on how to do it. Now, if you have not previously signed up for learn.parallax.com, and this is, by the way, just so you've got it before the workshop is over, you won't need this for participation's sake on Friday, because I'm just going to go here, show you the teacher resources, and you have to be logged in to get to them, or at least to get to the solution sets. So it's not crucial for Friday, but it would be great if everybody could either just go and log in if they already have are signed up with learn.parallax.com, or if you're not signed up, you will have received an email that Stephanie has either sent or will be sending shortly, inviting you to set up your account. And if you've never logged into learn.parallax.com before, and you did not see this email in your inbox, do check your spam queue. It might have ended up there instead. And that is it for today.
All right, I'm going to stop the recording before any questions.
Okay. Thanks, everyone.